page 346, and now we're going to take our exponential functions and do all the transformations from chapter 3 to our exponential functions. So it's going to be a little bit of a review. First of all, above this, I rewrote the k part on the right-hand side. We did that every time in transformations unit. We moved everything over to the right. Now, they have explained everything very thoroughly here. We're going to do it the same way we did before, just moving from left to right, dealing with our stretches and compressions first, and then our translations after. So at the top of page 346 on the side, I'm going to get you to write this question. We're going to graph y equals negative 5, 3 to the 2x plus 4 minus 7. What makes an exponential graph a little bit more difficult compared to the ones that we did in chapter 3 is that there's a number in our parent function. So our parent function for this one is an exponential function. Does anybody know what the base is of the exponential function that's given to us there? The base would be 3. Because here's our exponent x, the base is 3. And so this 3 and this x, that's part of your parent function. And what makes doing your transformations with exponential functions a tad bit more difficult is you get tempted by that 3 to do things you're not allowed to do. Some people think that 3 should be another vertical stretch. It's not. It's part of your regular graph. It does not affect any transformations. In fact, if we go from left to right here, we can label these just like we used to. This is a vertical reflection. Here we have a vertical stretch. The 3 does nothing. It's already in factored form. This would be a horizontal compression. Here we have a horizontal translation. And finally, a vertical translation. So a review. How did we do transformations? Well, first, we thought about our parent graph. Our parent graph, y equals 3 to the x. That's an exponential function. We know that it looks like this, going through the point 0, 1 and 1, 3 with an asymptote at y equals 0. So if we think back to our transformations unit, what did we do? We took the points on our original graph. We took 0, 1, 1, 3. We're also going to look at what happens to our asymptote y equals 0. We set up our arrows. How is this point going to change? Moving from left to right, we do all of our stretches and compressions first. So these two together, they would multiply y by negative 5. So above this first arrow, I'm going to write that I'm going to multiply y by negative 5. The horizontal compression here, remember that it's always the reciprocal for the horizontal. So here, we're going to multiply x by 1/2. So on this arrow here, I'm going to write x by 1/2 as well. What does that do to my points? Well, 0, 1 is going to change to be 0, negative 5. 1, 3, x by 1/2, that'll make this a 1/2. And 3 by negative 5 will be 1/2, negative 15. Next, our translations. This plus 4, that's going to go 4 to the left or right? Left. Good. And the 7 is going to go 7 down. So we're going to go 4 to the left and 7 down. 4 to the left would make this negative 4, 7 down, negative 12. 4 to the left, negative 3.5, 7 down, negative 22. If you have an asymptote at 0, and it's a y equals 0, nothing that changes the x is going to do anything to this because it's y equals. And if you multiply y equals 0 by a negative 5, it's still going to be y equals 0. The only thing that affects a horizontal asymptote at y equals 0 is if you move it up and down. Do we move things up and down? Yes. We move it 7 down, so our asymptote is going to move down 7. Now that we have all that information, we know where our new asymptote is, we know where our new points are, we can start to graph. I'm going to draw my scale like this. 1, 2, 3, 4, 5, 6, 7. There's my asymptote at y equals negative 7. I have to label the points 4, negative 12, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Okay, I think this is at negative 22. 7, 8, 9, 10, 11, 12, negative 12. So we need to label the points negative 4, negative 12, and negative 3.5, negative 22. My graph, because it's going this way, would have to go towards my asymptote here and go down forever that way. Still has the same shape that our exponential function had to begin with. But we had a reflection, right? We had a vertical reflection, so that makes sense why it's not swooping up, it's sort of swooping down. And so a review of transformations, what we have here is we have to recognize the parent graph within, that it's a 3 to the x. And I actually have had students in the past highlight or even take out a different color pen and circle that 3 and that x so that they don't make that part of their transformations. Very, very tempting that students like to do is they like to see this and they like to go negative 5 times 3. Ooh, I know negative 5 times 3. Negative 5 times 3 is negative 15. That's great that you know that, but you also have to remember there's an order of operations in math. Remember in grade 7 learning BEDMAS or PEDMAS, depending if they use brackets or parentheses? How many people learned PEDMAS with parentheses? Okay? How many people learned BEDMAS with brackets? Nobody learned REDMAS with round thingies? No? No? Okay. Could be. Anyways, exponents come before multiplying. So this 3 has an exponent. And you would have to deal with all of those exponent things first before you can multiply by negative 5. That being said, I'm going to make a bold prediction here. Somebody in this class is going to break that, and when they see negative 5 times 3, they're going to want to multiply negative 15. That's my prediction. You're going to try as hard as you can not to do that, but I think for someone in this class it's going to be just way too tempting, and you're going to do that on a quiz or a test. We'll see. I hope I'm wrong, but I think someone's going to do it. Once you realize that those are part of your parent function, then all the other numbers are your transformations. You can label them like we did. You can set up your original points, set up your transformations with stretches and compressions first, translations afterwards, and Also look at your asymptote. The only thing that's going to affect your asymptote is if things shift up and down. So when we go to example 2, it's the same idea. Here we go. It says use the graph of y equals 2 to the x. I'll quickly draw it here. Has an asymptote at y equals 0. Has the point 0, 1 and 1, 2. That's your basic graph. And we want to use that to sketch y equals 3, 2 to the x, negative x plus 2. So they really didn't need to tell us this first part. Most questions on your exam would just ask you to graph this section, 3, bracket, 2, and notice that this is not in factored form. So you might be very tempted to say horizontal reflection and move 2 to the left, but when we write it in factored form, factor out the negative, it's actually a translation of 2 to the right. I'm going to put a box around the 2 and a box around the x to say that's my parent function. So when I'm going from left to right, I have to describe what does this 3 do. This is our vertical stretch. Y values by 3. Next, the negative. Horizontal reflection. X values by negative 1. And finally, minus 2 goes 2 to the right. So look at our original points. Our original points on our graph, we had 0, 1, 1, 2, and an asymptote at y equals 0. Draw your transformations. First of all, stretches and compressions, we're going to multiply y by 3 and x by negative 1. So this is going to become 0, 3, and this is going to become negative 1, 6. Then our only translation is 2 to the right. So we get 2, 3 and 1, 6. The only thing that's going to affect your horizontal asymptote is if you had a translation up or down. We moved it to left and right, but we didn't move it up and down. So this asymptote stays at y equals 0. We can now graph. When graphing, I like to always start with the asymptote. So it's still at y equals 0. Then plot the 2 points. I've got 2, 3 and 1, 6. Joining those points, it's going down, so it'll have to approach the asymptote here and up in that direction. And we have our final graph. Now that we have that graph, we can go and answer some of the questions about it that they'd like us to figure out. Is it increasing or decreasing? It was decreasing. Okay? Since there's an asymptote at y equals 0, there's no x-intercepts. And looking at our graph, it looks like it's going to cross the y-axis, but it doesn't have a point that we've labeled. So how do you find a y-intercept algebraically? You set x equal to 0. If I set x equal to 0 and I solve, I'd have y equals 3 times 2 to the 0 plus 2, which would be 2 squared. 2 squared is 4 times 3. Our y-intercept is 12. The equation of the asymptote, state at y equals 0. Our domain for exponential functions is everything. And our range, y is bigger than 0 without the equal sign. Now, before I give you questions to practice on this one, I'm going to introduce you to a new number. Okay? It's been a while since you've learnt a new number. Are you ready for your new number? Here is your new number. Not to be confused with the old letter E that you used to know. You're familiar with the letter E? Are you familiar with the number E? It's on your calculator. See if you can find it on your calculator and tell me what it's equal to. Oh. Anybody find it? Yeah? Yes, 2.718281828. What do you think's next? 1828? No, you're wrong. It goes off weird after that. Sure looks like it should do 1828 again, but it doesn't. The number E is there. It continues on forever, random, just like pi. It's another special number, just like pi, that is irrational, but really important. So here we have the number E. And the number E is really important, in particular with exponential equations and exponential functions. And so that's why it's introduced in this unit. It becomes extra special when you take calculus next semester, right? If you haven't signed up for it, please do. And when you take calculus next semester, you find out that the equation y equals e to the x is the only function whose derivative is itself. Okay, right now you have no idea what that means. That's fine. But I'm sure you're super curious now. So sign up for calculus next semester or take it in university. But what we're going to do now is we're going to graph e to the x. Well, it's just a new number. It doesn't make it any more difficult than graphing 2 to the x or 3 to the x. How did you graph those? Well, you had the point 0, 1, and now we have the point 1, e, which is roughly 2.718281828. I should really memorize the next number. What's crazy about e is you just learnt it, and it does not take you very long to memorize 9 digits of e. You've known pi since probably like grade 7, maybe even grade 6. Do you know 9 digits of pi? Or just 3.14? See, it's like e is so much easier to memorize. So there's your parent function for y equals e to the x. Now you can do this on page 357, or yeah, probably 357, gives you lots of room. And then if we want to, we can now graph y equals 3e to the x minus 2. Well, you have your parent function. What do we have here? We've got a vertical stretch. Going to multiply y by 3. We're going to move 2 to the right and 1 down. So we can set up our arrows. Do our stretches and compressions first. take our points from our parent graph, which are 0, 1, and 1e. And then what happens when you multiply by 3? Well, you'd have 0, 3, and 1, e changes 1, 3e. Nice. It just sounds like a really loud 3. And then 2 to the right and 1 down, we'd get 2, 2, and 3, 3e minus 1. And since we did move it down, our asymptote's going to change to y equals minus 1. So when graphing, can you see that drawing the asymptote at y equals minus 1 is going to be no problem? For 2, 2, that's going to be no problem. But where do you put 3, 3 minus 1? Well, if you know that e is about 2.7, you can multiply that by 3, get 8.1, subtract 1, get 7.1, gives you an estimate of where to put that point. So then you could graph it with your points, 2, 2, 3, 3e minus 1, draw the same shape of an exponential graph going towards our asymptote just like before. And everything is the same. So, questions for practice now. 10 and 13.